All right, welcome everyone. My name is Madelon Hulsebos. I've been a postdoc at BITS and hosted at EECS in the EPIC Data Lab, where I was working with Aditya Parameswaran, among with the great folks in that lab, so among which Shreya Shankar, Wenjing Lin, Rachel Lin, and Xingyu Yi. And I've been really focused across multiple projects on retrieval systems for structured data. So that refers to, for example, tables, spreadsheet, that you can find in spreadsheets or relational databases, because I really think that this kind of task is currently missing from many systems, and it's really a critical component to couple LLM-powered, so large language model-powered query interfaces for factual data. Because everyone has so far been really focusing on, for example, text data or images, etc. So you see large language models, you see vision models, but people have been really overlooking structured data for a long time. So this is what I've been focusing on for 5 years and now really deep diving into retrieval systems. And why I think it's really important to do this well is because finding the right data for basic question answering, for example, through an LLM-powered interface, or for deeper analysis of data, this task is really not easy. So yesterday we had a great talk from David Barstow, for example, who told us about how hard it was to find very good data and capture that in spreadsheets. It was really a manual task for him to inform his investigations for journalism. And I think we have so much data everywhere, on the web, for example, that it would be very nice if we can help people to find the relevant data for a certain analysis easily, instead of doing, manual collection of data, etc. So,
yes, explanatory questions.
Of course, yes.
Are you saying that there's not a lot of structured data available on the web?
There is actually a lot of structured data available on the web, but also, in proprietary databases, for example, in companies or, governmental organizations. But really the task here is that we should be able to retrieve that easily. So imagine that you have a Google search interface, for example, to find the relevant data set, structured data set, for any task, which can be, just a simple question that we'll get to a few examples, but also for deeper analysis, for example, of, Donald Trump's financial statements, I think that David has been looking into. So there is actually a lot of data and we should be able to find it easily.
So the chatbots are really structured to look for figure out the next word as opposed to...
For example, but I think in conversation, we'll get to one of the examples there, indeed, where you are having chats with LLMs, such as ChatGPT. Then we should be able to connect ChatGPT, for example, with structured data to, for example, do fact verification over or question answering, and then retrieve the right factual information from structured data to enrich the LLM's memory, because LLMs, they can learn well from text data, but they don't have private data, for example, to their availability. And we'll get to some examples of that. But so in the first part, though, I want to focus really on helping data analysts, machine learning engineers to find the right data set for more deeper analysis. So for analytics use cases, or for example, training a certain machine learning model. In the second part, we're indeed going to look into how we can enrich large language model interfaces with structured data, and how to ground LLM-powered interfaces in structured data. So these are the two kind of retrieval use cases that we're going to talk about today. So starting with how we can help data analysts find their data for analytics tasks. And here I think there are, of course, quite some systems available from, cloud data warehouses, for example, who make, data in proprietary relational databases somewhat searchable. But still, these dataset search systems that we currently have are not really what we need. So we find that these current systems are not really flexible enough, because imagine that you're looking for a data set to forecast monthly energy consumption per household, for example, in the United States, until May 2025. Well, what you can do for this is to go to Google Dataset Search. So Google doesn't only give access to web pages, it also has an interface to find data sets on the web. So here you have a Google Dataset Search. I hope it's somewhat, you can somewhat see this. But what you typically have, you have some kind of keyword search box, as you are familiar with, particularly from Google Search, along with a set of filters that is fixed for all data, for all data sources. And then you can type in your keywords. So for example, monthly energy consumption per household in the United States that you think will help you to solve this task. So to build this forecasting machine learning model, for example. And then maybe you do some additional filtering for that. Well, if you do this, then you end up with 69 data sets, which is already quite well scoped. But typically in many, in the world where we collect so many different data sets, and that number of data sets keeps on rising and rising, it becomes, well, very tedious to go through, for example, 70 different data sets to really find the one data set that you need for a particular task. And now this is only 70 data sets, but very often there is such a high similarity between different data sets that you can end up with 1,000 data sets. So, if you are just looking for one single data set and you end up with 1,000 data sets, you just give up, or at least that's what I typically do. You just figure it out. And that's what we wanted to understand a little bit better. So what is really happening there? And why is it still so hard? And what are people doing to kind of overcome this bottleneck? So we surveyed 89 data practitioners that we recruited through social media, among our target audience, which is typically data analysts, but also researchers, but then really domain-specific researchers who do data analysis for their research. We also had data managers, machine learning engineers, and so on, across various industries, most commonly in tech, but also finance, health, research, automotive, education, etc. So it's quite a diverse population that we surveyed. And we asked them, how do you currently search? Well, obviously, they try to formulate some queries, some search queries, typically keyword search queries. So they try to think about, hey, what problem am I trying to solve? And what would be the data that I could use for that? I think what is interesting to see here is the second most common method. It says consultations with colleagues. And that is something, so I've been a data scientist myself as well. And this really resonated with me because when I was asked from a product owner, for example, to build some kind of machine learning model for a given problem, I had no clue what data I should use. So what I did, you go to your colleagues and then you ask them like, hey, what data can I use for that task? And this is what all the practitioners, well, almost all practitioners also said, like, hey, I go to my colleagues to ask them what data I could use for my task. So then you can think about data engineers or domain experts, for example, a financial analyst. You go to them and you ask them, oh, what data can I use for forecasting, I don't know, product revenue or something. But then, the financial analyst also says, I have no clue because I don't know what data exists in our databases. So, this is really a problem. So no one really knows what data you can use for these tasks. So that was an interesting finding that we had there. And then we also asked them about the challenges. So what, with the existing systems that you currently use, what is it making so challenging to find the data set that you need for a particular use case? And some interesting issues came up there. So for example, inconsistent naming conventions. So you might have seen, or you might have interacted with relational databases, and you have many databases with many tables, and then each table has, columns, and, typically these column names are not very descriptive of the underlying data, for example, or at least in the enterprise domain or in governments, etc. These descriptions can be, well, messy, as here someone pointed out, and very inconsistent across different data sets. So if you don't understand what the data is about, it's hard to match that, of course, with your actual needs. Another issue that the practitioners faced is that the granularity of the data is not clear. So imagine, the task that we were talking about prior to this slide is we want to do some energy consumption prediction on a monthly level. So then we need data that is on a monthly level. But the current interfaces don't surface that granularity of the data. So that is something that is currently missing as well. And one of the other issues that also came back is that there are just too many results from these initial dataset search queries. So for example, the 1,000 datasets that you end up with, that is just too much if you're just looking for one single dataset. There's no way that you can now easily browse through all those 1,000 datasets. And that's another maybe complementary issue, is that these existing search interfaces, they don't have the flexibility to narrow down this search. So you really have limited options to express your search need of your data. Yes, of course, yeah.
I'm curious if any of the survey two problems. One, the problem of language translation, multilingual components to data sets, and the other one is confidence in the data sets that are retrieved. How on earth, can I trust this stuff? So those are just two questions that jump to mind, but you may be getting to those later.
Well, yeah, no, I think those are interesting ideas. We haven't really, maybe our language, like the language across the survey, the people we surveyed wasn't so diverse in terms of language, or where you might face like language translation issues in it with these data queries. But that's also because maybe existing dataset search systems that provide an interface to public data. Yeah, but then if they also have like multilingual interfaces, then they typically do a translation on the query. So if you have, for example, a Danish query, then that might get translated to English, and then you can still, search English data sets for that, as well as Danish data sets, by not just executing the Danish query directly. Yes, yeah, I think that's an additional complexity probably to this, because then you would also need to translate the data set itself probably to really make it easy to understand for people in different languages. And the second challenge that you mentioned was, the confidence in the data. Yeah, so many people also flagged that understanding where the data comes from is also a challenge. So they want to understand, the lineage, let's say, of the data and the history of the data. That's not, that didn't came up that often, but I think that's more like an advanced like functionality that, goes even beyond the issues that, are the most basic, the basic and primary issues that we focus on now. But those are indeed, so also the data quality, indeed, you can also add like data quality validation, for example, to really figure out, oh, what is the quality of this data set? And that is something that we're looking into now as well. Yeah, so based on the findings that we had here, we have been working on like next generation data set search systems, because in the, in the world that we are in now, there are so many new tools available to us that can help us better find better find data sets, of course. Then you can think of, for example, large language models. But what should these next generation data set search systems really do? So what are the requirements for these systems? Well, first, we think it should be really task driven. So currently, all these search systems are more data driven. So you need to describe the data and then you can find it. But as we already said, no one really knows what data you need. You just know what you want to do with the data. So we need interfaces that start from the task and not from the data description, because the explicit data needs are typically unknown. Search systems should also be hybrid. So we want to search over the raw metadata. So for example, the granularity of the data, as well as the semantics. So you really need to have a robust search engine that is able to do translations, for example. So you want to have a semantic capability there and not just querying on the syntax, so not lexical search. These systems should be way, way more iterative than we currently can do. So we need to go beyond like a simple search box and additional filters. We really should help users to drill down further and further to get to their data set of, that they really need to accomplish a certain task. And then finally, another requirement is that these search systems should really make the results interpretable. They need to allow people to understand what the differences are, for example, between these different data sets. They need to service the quality of these data sets, for example. And here, I think we can really study more the information retrieval principles to do that better than we currently do. And yeah, I think by doing that, we can also make the whole result set more navigable, but also more digestible to really not overwhelm users too much, as current systems do. So we have a few ideas of how we can accomplish that. And I want to highlight one of them now, and that is a task-driven search with hypothetical schema embeddings. Because remember, some user doesn't really know what data they look for, but we have large language models who might have that knowledge. So we start off here with a task-driven query. So instead of describing the data that you need, you only say what data is needed to train a machine learning model to forecast demand for medicines across suppliers. That is the machine learning task that we have to do, and that is the query that we specify. Then we use a large language model to generate a hypothetical schema. So given this task that you have to accomplish, instead of trying to figure out with consultations of coworkers, you just ask an LLM, hey, what data can I use for that? And then the large language model, so for example, ChatGPT, outputs a hypothetical schema, namely 2 tables. One table is a medication table with medication ID and medication name. And the second table is a sales table with medication ID, because then they can be linked together, a supplier ID, date, and the quantity sold. And apparently, if we have these data sets, we can accomplish this task. So this is a way to kind of improve the specification of the data set that you would need. So what we can then do is, instead of retrieving for this initial query, we retrieve based on the generated schema the relevant tables that we need to implement this task. So from our source tables, which we might have in our relational databases, we then retrieve tables that are similar to this medication table and our sales table. So that is what we really need. So then we use really the kind of generic knowledge stored in large language models to help us understand what data we need. Another a technique that we're currently exploring with is to how we can break down these queries more. So we have now these like search bars, like search boxes, and that is it. So you have a very complex data need typically, because we've seen, for example, granularity, we've seen the semantics of the data, maybe there is some kind of time range, but you're now required to put that all in this one single search box. So for example, we asked practitioners to formulate an example query that they want to execute. So here they came up with, okay, I want to find a data set to train a medicine forecast model, and it should contain these and these columns in these tables. The data should span 2 years with some specific date range, and the fact table should be at a particular granularity and contain at least 20K records. Well, that's a pretty complex search query that if you put this into Google Dataset Search, it won't be able to match that to the data sets in Google Dataset Search. So what we need to do is we really need to break this down step by step. So as we said, we can use these hypothetical schema embeddings and really start from the task. So I'm looking for a data set to accomplish a certain task, and then it retrieves these tables through the hypothetical schema embeddings that we just saw. And then we have our initial set of relevant tables. And then we break this down, like every requirement per requirement, over the metadata, for example, until we find the data sets, or at least a small set of data sets that is relevant to our use case. We have some other techniques, but we don't, I don't want to go into too much detail here, but the core idea here is that we can do this very flexibly. So we can, instead of just having one search box and then a few filters, we can continue pruning the space until we find the few data sets that we can actually understand, and then figure out which one we can actually need. And there's some other advanced LLM-powered techniques in there, such as text to SQL, where, because this is all natural language, of course, that you see here. So what we can do is we can take, spend 2 years and translate that to a SQL statement, which is then executed on our metadata table, let's say. But these are more like advanced techniques that we use to really drill down deeper and deeper into our data zoo, let's say. And of course, yeah.
You say we, you mean the artificial intelligence program, or
yeah, so eventually the user is really in charge. So the user leads the system to kind of prune through the space. So it's really a collaboration, I would say, between the two. But that's actually a good point, because how do we bring the user, how do we collaborate with the user and the engine? And that's through an interface. So that's another component that we're working on currently, is to build interfaces that guide a user to specify their query, iteratively. So that's another thing that we have been working on. And we really think that we should have proactively. So we really want to guide the user proactively to find, to specify their query. So currently, all these systems are just, you end up in this, complex interface. You have no clue what you can do with it, and how you should then formulate your query. So we really want to focus on, using a large language models to kind of prompt the user to better specify their search query. So that's something that we are looking into now. And well, this is, I hope this is somewhat to be seen. But what we have here is that at the top right corner, we have like the query blocks, let's say. So for every query need, so for example, it should span over 2 years, the data. It should be about medicine. It should be at least 20,000 records. And we had some other requirements. We break that down and have very a good overview of the total query bit by bit. So we really guide the user through a conversational chat interface, of course, nowadays, to specify their query iteratively. So this is currently the interface that we are working on, but this is really something that we are still building out. Yeah.
How broad is the search domain? That is to say, are you just somehow or other searching for the Google data sets domain, or is there some other, is it just sort of wide open? And then the other one, as you mentioned, the vectorization of the data sets, and I'm curious as to what is being actually vectorized for the similarity search.
Yeah, those are good questions indeed. So to the first question, our goal is to facilitate search for any set of tabular data sets, let's say. So this can be data sets in Google Dataset Search, but it can also be within a private organization, for example. So I think what is really nice is that instead of having, a very constrained kind of interface or kind of properties that you can query over, we can search over any property because we kind of abstract away from these filters, for example. So we're not fixed to specific metadata that is available within, for example, Google Dataset Search, but this can work for anything. And you can, tag this or kind of connect this engine to any metadata that you have available. So you can search any data set or like any collection of data sets, let's say. Yeah, so it should be really, really flexible. And then to the second question, I think I removed that, but what we now have, so in terms of what you embed of a table, that's really an open question, and we will get to that in part 2 as well. But it's I think now what we do is we embed just the header, so the column names, along with a sample of rows. It's just the first attempt to see how it works, but we are iterating on, okay, how many rows should we include there? Does it not distract the embedding? So what is really the relevant signal that we want to preserve in these embeddings? But that is what we currently do. And that's also for generating these hypothetical schemas. We now just generate like column names, for example, but we can also generate like sample values or example values of these columns, because in the end, if you can embed like sample rows of your real data that you want to search over, then you might also want to add some like example rows to improve this like similarity there. Does that make sense?
Oh, yeah.
Yeah. Yeah, so this is I think really how we can move towards the next generation like dataset search systems. But there is, I think, more to be done there. So this is definitely a work in progress at this moment. And we're just experimenting with how we can do this better and how we should really guide the user. That's an open question at the moment. So I now want to move on to part 2, where we will be talking about how to ground like large language model powered query interfaces in structured data. So then you can think about, hey, if I have a certain question and I want to ask that to ChatGPT, how can we connect ChatGPT with structured data? That might be structured data from the web, or it might be structured data from, that we have in, proprietary databases, let's say. Are there any questions about part 1 about dataset search for more analytics use cases? All right. Then I want to move on to part 2 and how we can ground LLM-powered query interfaces in structured data. As said, sometimes we want to ask an LLM really complex questions. So, for example, here, parents might wonder, what is the highest eligible free rate for K-12 students in the schools in Alameda County? well, that's a pretty hard question to ask an LLM. So among with lots of interpretation and context and some guesses from ChatGPT, I want to focus on this part of the answer that was generated by ChatGPT on 6 October. It says to determine the highest free rate specifically in Alameda County schools, you generally need data from specific school districts or schools in the area, as this rate can vary widely depending on the socioeconomic demographics of each district. So this is interesting, I think, particularly as it points out that you need specific data that gives this, that would be able to give an answer to this. So this is not something that is widely available on the web, for example. So the question then is, how do we ground language models in this specific data, right? And there is a paradigm for that, which is called retrieval augmented generation. I don't know if you have heard from that, but given, for example, ChatGPT, you can enrich ChatGPT with other external knowledge sources. So for example, raw text corpora or knowledge bases, maybe images, audio, and video. But to answer this question, you might wonder if this is really what we need. So can we really answer the question with, I don't know, raw text corpora? That's maybe not really the most efficient and most suitable way to answer this question. Instead, what we can do is have, see if we can find tables that, have data across, all the schools in Alameda County and the like free rates. I think this is about, you probably here know that better than I, but I think here, this question is about lunch discounts. That's something that I wasn't familiar with because I'm from the Netherlands, but ChatGPT was able to contextualize that for me. So that was the hidden part in the answer. But yeah, to answer the question, I think we should really connect ChatGPT like LLMs with relational data. And that is really currently missing in the retrieval augmented generation landscape. So if we do that, and this is actually what I found out, then we are able to actually answer this question. We do need, of course, access to that, these data sets. So that's one thing to figure out, but in general, we can do that. So here, I want to really motivate why we actually need to extend retrieval augmented generation systems by enabling RAG over structured data. Because a pattern that I've seen in generative AI research, but also like representation learning and general machine learning, is that no one really has been caring about structured data. So everyone is really focused on text and images, etc. But in practice, everyone is caring about structured data. Because in all those organizations, hospitals, etc., there's tons of tables, and we need to be able to, do something with that and get our insights from that. And why I think we should be doing that is because structured data really serve high value insights. Because structured data is typically up-to-date data, it is very domain specific, and it contains facts. So this is something that we are currently exploring. And to give you a little bit of an idea of what such a RAG pipeline looks like and what kind of queries you can facilitate with that, here are some example queries that we can, we retrieve from actual data sets of structured data. So for example, which urban Japanese prefecture is not associated with thorny trees? Apparently, that's a question that is connected to some table that you can use to do a table lookup to answer this question, but also more aggregate questions. So for example, for fact verification, you might say Shane Hall ran a total of 190 races between the year of 1995 and 2008. This requires lots of filtering of the right data, like the right set of rows, as well as aggregations, because you need to sum over those rows, for example. And then, of course, you need to compare to check if this, this might be an LLM generated response, for example, or like a statement from an LLM, then you need to compare if this answer is actually true. But also our initial question that we were talking about, what is the highest eligible free rate for K-12 students? That also requires aggregation over structured data. And this might, maybe we'll get to that later, but this can be quite complex actually to do. So what does such a pipeline look like? Well, here we have our question. So we have a user with a question in mind. And then we want the system to contextualize and interpret this query. So we wanted to figure out that this is actually about meal plans and discounts of lunch. And then with that interpreted query, we want to retrieve the relevant tables that can be used to answer this query. And then if we have found and identified the relevant tables, what we then do is we put that into context of an LLM, and then we generate an answer given the table and this question, we generate the answer to it. This might require some execution of code, for example, SQL, because you need to aggregate over certain rows, for example. And then we end up with a response there. So we've been looking into in the literature, people have been looking into how you can interpret these queries, how you can enrich queries with more context, with all kinds of metadata to understand it. And people have also been looking into the generation. So how can we, for example, generate SQL code to execute on some database to answer this question? But what I'm really interested in, and what I think is really difficult, is actually this retrieval part. So how do we connect this question with the relevant data instead of assuming that the user already knows what the relevant data is to answer this question? So our question that we've been looking into is here again, how do we retrieve the relevant structured data for this? And retrieval is really difficult, but crucial. And this is a quote from Wenhu Chen from the University of Waterloo, that keep in mind that a good RAG, retrieval augmented generation system, is really hard to build. Typically, if your retrieval system is mediocre, the retrieval can easily distract LLM. So you can imagine if you retrieve the wrong data, the LLM will definitely not be able to give you the right answer. And there's still a long way to go. So this is really an underexplored terrain. And it's also really difficult, as he also pointed out, because the retrieval and generation complexity, so kind of the complexity of the whole system and all these steps in it, really depends on the complexity of the query. So maybe you can answer a query with just looking up like one single table, but it might also need like multiple tables. It might need an entire relational database, for example. And how do you then link all those tables together to be able to guide an LLM to answer the question, for example? So these are some important grounds to explore, but there are tons of questions that we should be studying here, actually. So for example, what does the task actually intend to do? Is there some fact or some statement that we should fact check, for example, or is it a question, or is it some like analysis that we need to perform? So should we generate SQL? So this is something that we should figure out. But then indeed, how do we process the data? What do we embed here? What do we put in such embedding? So you have, of course, tables. So just, some header and rows, but there might be metadata as well that can help to provide more like semantic information about this table. Because you can imagine that like text documents, language models are very good at understanding these text documents, but tables typically contain like numbers. It has no clue about that. So you need to have like in your embedding to perform the retrieval needs to kind of surface these semantics of these tables well. So these are open questions that we are looking into, but there are some other questions as well. So for example, which data source to retrieve from and when? So you can imagine that you have like within an organization, you have text documents, you have a set of images, you have tables. You need to understand which data source to talk to for which query. So that is another open question. So some of the methods, so we are now focused, of course, on purely table retrieval, so structured data. And some approaches have been taken there, or some approaches that we have been looking into so far. And that is like typical approaches. So BM25 and TF-IDF, I don't know if that rings a bell here, but that's like sparse lexical representations, basically based on term frequency in documents. So this can be tables, this can be PDF files, and then how often certain terms appear within a certain document relative to all the documents in this corpora. So that is a very common and typically robust method to retrieve from the source corpus to retrieve from. So what you then do, you vectorize all these documents, and then you vectorize your query, and you compare like your query input maybe with some kind of dot product or a cosine similarity between all the documents in your corpus and your query, and then you just return the most similar document there. Another approach here is to generate metadata. So for example, a summary. So I just provide, I use an LLM, and then I give my table to the LLM and I ask it for a summary, and then I embed that summary. That's also one option that, for example, Llama Index has been using, which is a common, an open source tool. I think it's still open source for RAG use cases. And then you embed, for example, this summary, which typically contains more semantic information along with the table. And then you do this comparison based on the query and these like enriched table embeddings, I would say. But you can also say, okay, I just take my query, I embed my query with some model from OpenAI, and I embed the tables. I just take, for example, the headers, I embed that with some model from OpenAI, and then I do the similarity search. And I refer to that as naive embeddings, but this can be actually pretty effective, as we show in a bit. But yeah, if you have all your kind of representations of your documents and the queries, then you simply perform a similarity search. So for a new question, you embed that one, and then you retrieve the top K relevant or most similar tables from your retrieval corpus. So this is what retrieval systems, retrieval components now look like typically. Yeah.
I'm sorry to keep asking questions.
No, that's great.
So fascinating. One of the problems that we encounter a lot is different encodings in similar columns. So date, for example, might be year, month, day, or it might be month, day, or it might be year, and they might throw an extraneous asterisks seem to be very common in some of the data that I work with, and then little annotations in the data tables itself. Do you do are you thinking of doing cleaning at prior to embedding, or has this come up? I mean, it sounds like, some of your structured data is really well structured.
Yeah.
I've got poorly structured data, or messy, dirty structured data.
I think, yeah. So we should definitely study also how robust these methods are for certain levels of messiness, because indeed, in practice, you have dirty data, you have missing data, and all kinds of inconsistency across different encodings. Indeed, typically these models now, the current models, are able to figure that out. So I think what is nice about large language models is that they have been trained over so many data documents and so many inputs, that it has somehow figured out that some European date formulation is actually the same, maybe, but it can still be mistaken, because sometimes you have 10-10 or 10-9, which is 9 October here, but which is 10 September. Yeah, of course. But then there might be some other context in the table that kind of can hint to the language or like the source of the table that can somehow then disambiguate that. But this is not something that we have intentionally studied now, and we just hope that it's that it can figure it out. But these kind of like semantic ambiguities is something really hard currently, I would say. But we can remove certain, we do some light pre-processing to clean it up, I would say. Yeah. But this is definitely something that should be stress tested. So yeah, that's also something that we have been thinking about, like how robust are all these methods, and what can they indeed understand these different like inputs and different levels of messiness, and how effective are these methods that we have here?
So this is really interesting, and is this working?
I think it's to cast for Zoom.
Oh, okay.
Yeah.
And I am a researcher in generative AI, and I work in the text to image sort of space. So I have some work with LLMs, have some work with computer vision, and I find this really interesting. And I've been looking at data security in the last few months. And I wanted to ask you, so given some of your embedding and retrieval strategies that you're sort of outlining, how would you address efficiency at scale? So I start to think of like, I think that's a longer term question, and I have many other questions before that, but I'm curious if just looking at structured data, how would scale come into this picture for you?
Oh, that's an interesting question. That's definitely, so what I'm working towards is that we're doing a benchmark to indeed understand, how efficient are they? How robust are these current systems? Which embedding model can figure out, messiness across data, or not so descriptive variable names, for example. In terms of efficiency, so these more like lexical representations are very efficient at this moment, because these larger models take a bit more time to embed. But this is all done offline. So you just embed all the data once, and then you do the retrieval. But I do think that these more heavier models are more accurate at inference time, so at retrieval time, but they also are more inefficient for sure. Yeah. Thank you. So that is definitely kind of a trade-off that I think should be made. For data search, I think that's no issue, because now it takes them weeks to find the right data set, because there are so many consultations with people. If you just have like a question that you want to have answered, indeed latency is super important. You just want to get a question right away. So that is, how to do it more efficient, I think is something that we should be working towards and to improve on for sure. Because I think now we're using, for example, we're benchmarking this. So I'm going to introduce a benchmark soon, and we're using OpenAI embedding now, but I think there we also can figure out like, hey, maybe we can use a smaller embedding model, and then that might already be sufficient here. And we definitely, so one thing that we're doing is not providing full tables into the context of an LLM at generation time, for example, because these tables are huge, especially if you consider relational databases in practice. You typically have like a bunch of tables, and they are 10,000 millions of rows. Well, you shouldn't fit that into. So that's something, and then you need to do extra filtering on these tables indeed to figure out which rows are relevant, for example.
Context has to be like
Yeah, exactly. So this is definitely something that needs to be researched further.
Sort of related to the idea of efficiency, I'm assuming this data is behind an SQL interface, and it's basically staying there, and it's not being brought into the LLM as a permanent, part of the LLM. So the fact is, this data probably belongs to some company that's providing the interface, and you're likely to be, having compute time issues of the use of resources by these companies. If you're really automating all of this and tending to dump a lot more data with with this type of interface versus an actual human user, you're going to have companies that get overloaded and that are going to be upset about having their resources overloaded.
Yes, yeah, but I think the nice thing about retrieval augmented generation is that you can say, okay, I want to have a private model. I want to keep my data private, and I only want to enable, you know, users within the company to access certain data, for example. And then you don't have to train a model, for example, on that data per se, but you can do this retrieval offline. What is the time actually? Is it already what?
12:56.
Oh, okay.
So,
Let me need then quickly get through the, yeah, if that is okay. Does it answer your question?
Well, you don't see it as a problem of companies objecting to the use of their resources under this mode versus a user's typical.
I do think,
process.
especially for structured data that typically contains, you know, sensitive company data, for example, it's definitely data privacy is definitely a concern. So then you want to probably work with like local models and do this locally within a company. So you don't want to give any access. You don't want to leak any information into a model that is trained on it. So for example, OpenAI has an enterprise user model as well. So then it doesn't train on your data, for example, but it might still not really like this. But that's definitely a concern. So maybe to wrap up on what we've been doing here, we've indeed built a benchmark to better understand, you know, which methods are effective for which data sets, which tasks. So we have integrated several tasks, so question answering, fact verification, text to SQL, and integrated all the relevant data sets from that. And then we've built a benchmark where you can just implement a retriever and do the whole evaluation of the whole pipeline end to end. So from like data extraction to generation, that is all included, and as is the evaluation further. So we have some interesting, so this is a huge table that you have here, but I'll walk you through quickly through some of the insights. And as opposed to text documents and RAG over text documents, BM25 DF-IDF really is not effective for structured data because structured data typically doesn't have that kind of descriptive semantic richness. So I really advise against using BM25, for example, as representation for retrieval. As you can see here, so on this one particular data set, which has very descriptive metadata, it performs really well. But if you have data sets that have, you know, less descriptive tables, for example, these representations are really not that effective. So as he pointed out, you know, what do you actually put into an embedding? And this is really an open question. But what we found there is that actually embedding like lots of rows along with the header can really distract the embeddings. And this is definitely something that we should be working on. All right, so there's still really a lot to explore. So what we should be embedding to perform this retrieval, how do we route to the proper data source for an incoming question? But we also should really be stress testing these systems on more challenging tasks and data sets, you know, and to perform these methods and systems in like real relational databases. And this is also what we have on the roadmap for this benchmark. So yeah, Target is out today. So this is the benchmark, and you can find it on targetbenchmark.github.io and evaluate, you know, custom retrievers for end-to-end, like insight generation over structured data. So with that, I can now finally conclude. Sorry for going a little quiet over time. But I hope that it's clear that we should be really focusing on retrieval because it's such, you know, so critical component, and especially retrieval over structured data. We've been talking about data set discovery first, which now requires, coworker consultations, and existing interfaces are very inflexible. So we proposed a few methods for that, as well as interfaces to really guide a user to iterate on their search query and break down the whole search space to find the right data set. And we've also been discussing how we can ground LLMs in structured data, where we have introduced Target, which is the first benchmark for RAG for structured data. And this is really work in progress. So, any thoughts on that? Definitely got some interesting questions already over the course of this talk. So that is also something that we will be, taking into account for the next versions of Target. Thank you.